In this video, we're going to go over how to do the calculations for a weak base strong acid titration. Thankfully, this is pretty much the same process as the weak acid strong base titrations. First, we need to do some stoichiometry, figure out our limiting reactant, figure out what concentrations our leftovers are in, and then we need to set up a rice table so that we can calculate the pH. So first of all, I need to figure out what's in my beaker. I've got some ammonia and some hydrochloric acid, where the main portion of the hydrochloric acid is going to be the hydrogen ion. So I'll write out my reaction to be NH3 plus H plus yields NH4 plus. Now, before I really get started in this fake rice table, I need to know my mole amounts for all of these species. So, we'll take the 25 milliliters of the ammonia, which honestly is the same thing as 0.025 liters. And we'll multiply that by 0.1 to get 0.0025 moles for starting ammonia. Then we'll do the same thing for 20 milliliters of the acid. 0.02 multiplied by 0.1 is 0.002. Then we just have to use our excellent human brains and figure out which one of these is going to be our limiting reactant. Obviously, we just have a little bit more of the ammonia than we do the H plus ion. And because this is a strong acid, this is going to react completely, which means all of my moles of acid will go away. Most of my moles of ammonia will go away, and I will be adding a bunch of this ammonium ion. Okay, so now we just need to subtract away that 0.002 from the ammonia to get that little smidgen of moles left, and we keep the same number for the ammonium ion. And now we have the moles left over for our important species. To get ready for our rice table, it's a really good idea to take these moles and change them into concentrations. To do that, I need to add up my two different volumes that I've put together to get a total volume to divide them by. So we'll do 20 plus 25 milliliters is 45 milliliters. So I'm going to take both of these numbers and I'm going to divide them by 0.045 to get these values into molarity. This leaves me with 0.0111 molarity for the ammonia and 0.044 forever molarity for the ammonium ion. Now we just need to set up a proper rice table to find the pH. Now that we know what species are left over in the bucket, namely ammonia and its conjugate acid, ammonium ion, I can set up my reaction for a rice table. Before writing a reaction, I consider which one of my species is a better acid or base. So when I look up at the values for the ammonia species or the ammonium ion species, I compare their Ks. The NH3 has a K value, or rather a Kb value, of 1.8 times 10 to the negative 5, which means that the Ka value for the ammonium ion is 5.6-ish times 10 to the negative 10. The species with the larger K is generally how that species will behave in water. So if ammonia has a bigger number, the base form of this, the ammonia, will act as a base. And we'll write out NH3 reacts with water in an equilibrium fashion to produce a small amount of ammonia ion and hydroxide. Now we're going to assume at this moment that we're starting with no hydroxide in our reaction because we just added some strong acid here. So all we need to do is fill in our initial concentrations from the first half of our problem, which were 0.0111 and 0.0444. And then realize that if there's a 0 here, we're going to be subtracting some x from this side and adding it to both sides. Now since the K value is so small in comparison to our starting amounts, like literally 100 times smaller, we can assume that the minus x and the plus x for our larger species is going to be insignificant, though the change for my hydroxide will definitely matter. Now, let's set up the Kb expression, which should be equal to the ammonium ion on the top multiplied by the hydroxide. Again, products over reactants for this part. And then we just need to plug in our numbers. 1.8 times 10 to the negative 5 equals 0.0444 forever times x over 0.0111, and then we just need to solve for x. And when you punch that into a calculator, you get that our x value is equal to 4.5 times 10 to the negative 6. And then we really need to remind ourselves, what does x equal? X in this case is the hydroxide concentration. So if we take the negative log of that number, then you end up with a pOH value of 5.347, which means if you do 14 minus that guy, you'll get a pH around 8.653. And that's pretty much how you handle it for a weak-base strong acid titration. The mathematical algorithms are pretty much the same for both types of calculations.